All right, so here's where things get a little sticky, is we're going to be getting into conditional probability and independence. These are the things that you need to be able to do at the end of this unit. We're going to spend 2 days on this unit. Pause and write this down if you so desire. All right, so let's talk about how conditional probability is different than what we've been studying up till now, which is just basic probability. So let's say you roll a die. You roll a 5. You want to roll a 5. Chances of rolling a 5 are 1 out of 6. Doesn't matter what you roll on that die. If you roll the die again, your chances are still 1 out of 6, and it keeps going. The die doesn't remember. Picking a card is different. Because let's say I want to know what is my chance of what's my probability of picking a king? Well, on my first draw, it's 4 out of 52. But if I just pull a card out and do not put it back, then my odds change significantly on the second pick, and they depend a lot on what happened on that first pick. If I do pick a king on my first pick, then my chances of picking a king on the second one are 3 out of 51, because there's only 3 left in the deck. On the other hand, if on the first pick we didn't pick a king, then my chances of picking a king are 4 out of 51. So if I pick a king, my chances of picking a king a second time go down, but if I didn't pick a king, then my chances of picking a king go up. And this is what's known as conditional probability, and what we're going to be talking about in this unit. So the probability, this is the basic gist of it. We're saying, hey, something has happened. Does that affect the probability of something else happening? And so we're going to be seeing probabilities here, conditional probabilities. So the probability that one event happens given another event is called a conditional probability. And we write it like this. You can see here, so the probability, if we see this is the, you would read this as the probability help if I could spell, of A given B. So, and the one up here, this is the probability that B given A. And so what does that mean? How do we apply that? All right. So first we're going to define 2 events. The first event is that, hold on one second. If you go to page 314 in your textbook, which you can pull out, you should have at home, they're talking about, I don't think you need it for this, but if you want to follow on, that's cool. The students at the University of New Harmony received 10,000 course grades last semester. The two-way table, shown here, breaks down these grades by which school of the university taught the course. The schools are liberal arts, engineering and physical sciences, and health and human services. And it says that this is an actual thing. It's based on a real university, but they simplified it for clarity because most universities have more than 3 schools, and it gets a little messy. So we're going to define E. Oh, hold on. Sorry for the interruption.
Miss Gallagher, Katie Gallagher, please report to your classroom. Miss Gallagher, please report to your classroom. Thank you.
I hate recording these videos after school. All right, so EPS course is Engineering and Physical Sciences, so it's this one. So, and we have divided into A's, B's, and below B's. So, find the probability of L, that the grade comes from an EPS course. So, what we're going to be looking at, the probability of L is, these were the grades given to an EPS course, and these were the total grades. So the probability of L is 6, if we chose one grade at random from the student population, the chances that it would be an engineering wait, class is that right there. Oops, sorry, I just realized I made a mistake. That's the probability of E. Sorry. This is the probability of E, the probability that you had an engineering course. That's not what they asked. They asked the probability of L, that a grade is lower than a B. So that's going to be 3656, this one, out of 10,000. Very important how we define our variables, or 0.3656. So that's basic probability. That's what we've been doing up until now. So what we're going to do is we're going to find the probability of E given L. And the key thing here is this definition right here, which is the grade comes from an EPS course and is lower than a B. So this is the probability that your engineering course, given your grade, was lower than a B. So there were 800 out of 3656. So the probability of E given L is, approximately 0.219. Oh, 0.2188. All right, cool. Because we're getting the probability of E, which is given it's an engineering class, but we're only saying below a B. This has already happened. All the grades are below a B. So find the probability of L given E. This is the probability now of the probability of, let's go back to our definitions, probability, sorry, I went too far. Probability that the grade is lower than a B given your engineering class. So now it's 800. Right, it's the same number of grades given out, but now we're only looking at grades that were given out to engineers. And sure enough, we get that. So given that you're in an engineering class, the chances that you got below a B were 50%. Obviously, the people in the engineering and physical sciences grade a little bit harder than the general population. Remember, your probability of getting a B, we said, was 0.365, right here. And so being in an engineering class means it's more likely that you'll get a B than if you were just a general student at the university. Which leads us to our next thing, independence. When the knowledge that one event has happened does not change the likelihood that another event will happen, we say these two events are independent. Two events, A and B, are independent if the probability of one event has no effect. So if the probability of A given B is still the probability of A, and the probability of B given A is still the probability of B, then we say that those two events are independent. So the probability of getting a B and the probability of, so we would say the probability of being in engineering, or sorry, being in engineering in this last example, being in the engineering and physical sciences and getting below a B were not independent because the probability of L, which was 0.365, does not equal the probability of L given E. It's the first one has to match if there was no conditions on it. The first one has to match if there's no conditions on it. So let's look, oops, sorry. Oh, okay. Thought I had erased this text. All right, so are the events male and left-handed independent? So we're going to define M as, let me make sure I get the notation right here. So we define our two variables. M is, so here's our two events. M is male and L is left-handed. And so what we need to find is that we need to find the probability that you're male, but we also need to find the probability that you're male given you're left-handed. And these two have to be the same for something to be independent. So the probability of male is, there's a total of 23 males out of 50. So the probability of M is 23 out of 50, or 0.46. And the probability of being male given you're left-handed, all right, so left-handed has occurred. So now we're working exclusively in this. And so the probability of being male given that you're left-handed is 3 out of 7, or approximately, well, they went about a different way. They did probability of left-handed and probability of left-handed male, and those aren't equal. But these aren't equal either. 3 out of 7 is 0.428. Now they're close, but they're not equal. And in mathematics, we take the equal sign very, very seriously. So unless these two are equal, we cannot say the two events are independent. And so they did the same thing, but they did probability of left-handed given male versus probability of left-handed. But these two aren't equal either, therefore they're not independent. Because remember, coming back, both of these need to be true for the independence. To disprove independence, we only need to show that one of these is not equal, and the whole thing breaks down. Now, you're going to find conditionals much, much easier if you learn to use the tree diagram. Tree diagrams are going to make this a lot easier. And I've shown this before. What is the probability of getting 2 heads? Right, and we've done the sample space, but if we do the tree diagram, once again, right, you do each possible and you write the probability on the arms. And the probability, to get the probability at the end of the outcome, you just multiply down the arms. Now for tossing a coin, it's not that complicated. But let's look at a more complicated example. But before we do that, we need some definitions. The idea of multiplying along branches in tree diagram leads to a general method for finding probability of A intersect B, which is probability of A and B, that 2 events happen together. Remember, the intersect is and. If you see union, that's or. So the probability that events A and B both occur can be found using the general multiplication rule. This is the rule, and this is on the formula sheet, and you don't want to use this at all. You want to make a tree, and you want to do a tree. So the Pew Internet and American Life Project finds that 93% of teenagers use the internet, and that 55% of online teens have posted a profile on a social networking site. What percent of teens are online and have posted a profile site? So first, we got to see if they use the internet. So, ready? We start our first one, and this is online. None. online. And this is 0.93. And this is 0.07. Because the two parts of the branch, it either happened or it didn't. And so each piece of this branch here always has to add up to 1. Then, of these teens, 0.55 have a profile on a social media site. And that means that 0.45, no profile. So the probability that someone is online and has a profile is 0.93 times, I'm sorry, I should do it like that. Remember, we write the probabilities on the arms. Times 0.55. And so what you can see is this. And they do it using the rules, where we will do much better on our own using the tree. The tree will set you free. And so we would say this is 0.5115. Now we can get each branch, the end of each branch, which is 0.93. So this one is 0.4185. And this one, if you're not online, you can't have a social profile, is 0.07. And all the branches at the end of your tree, if you add this, this, and this up, will always add up to 1. So we're going to be getting into doing a bunch of these tree diagrams in class and really getting into the nitty-gritty and banging out a bunch of these. But that's the video for today. I know there's a lot of notes, a lot of density there. You may want to go back and rewatch certain parts of this. I will see you next class.